Here's another example of an algorithm that falls in the same category of stochastic motion planning algorithms. This one is called Probabilistic Roadmap, or PRM. Let's again draw ourselves a little tiny toy example with Q1, Q2, this is our workspace, and let's put some obstacles in here. Okay, what's interesting about this algorithm is that you can, one variant of it, which is shown here, what you're doing, you're building what's called a roadmap without even necessarily having a start and a goal. So what we're going to do is sample a number of random points in C space. I'm going to say 10 here because you just need to select a threshold. But even with just as few as 10, I think we'll get good results. And then what we do is we connect those points to as many other points that we've sampled as possible. So let's do 10 of them. So 10 and 7. So let's use blue to draw the roadmap. So if this is 10 and 7, this is the first point on our roadmap. Then we get 4 and 7. So 4 and 7. And you always connect every new point with as many points that you've already sampled as you can, as long as the straight line doesn't intersect any obstacles. Then we get 6 and 4. So 6 and 4, that's going to be inside an obstacle. So keep going. 4 and 2. Let's say this is 4 and 2. OK. 5 and 1. 5 and 1 is right here. 7 and 6. 7 and 6 right here. Does this go? Let's say it doesn't. 6 and 6. 6 and 6. So right here. 6 and 7. So maybe right about here. And we keep connecting. 0 and 4. So we're going to be here, and we can connect to all of these. I'm not necessarily going to draw all of the connections, just because it gets very busy. 3 and 6. So let's say that 3 is right here and 6 is right here. And again, you'd have a bunch more of these. OK, how many points do we have? 1, 2, 3, 4, 5, 6, 7, 8. So let's do 2 more. 2 and 8. So 2, let's say 2 is right here, and 8, let's say this is right there. So we can connect like this. And one more, 8 and 2. So maybe right here. And we can connect like this. OK. So that's it. We stop. This is our roadmap. Now somebody is actually telling us this is your start and this is your goal. So now somebody's giving you a start and a goal. So let's say again that the start is random. So the start is going to be 1 and 1. So somebody is asking us to start from right here. OK. And to get 2, 2, and 3. So let's say the 2 and 3 is inside an obstacle. So obviously nobody's hopefully going to tell us to go inside the obstacle. So let's sample another point. 2 and 7. So somebody is asking us to get to right here. How do you do that? Well, first, from the start, you try to connect to your roadmap. And in this particular case, really the only connection that we have to the roadmap is this. If this obstacle is not drawn as sloppy, then maybe we'd have another connection down there. We connect the goal to the obstacle, to the roadmap, as fast as we can. So this is the closest point. So now we have a start point that's on the roadmap, a goal that's on the roadmap, and this network of lines that we know are all collision-free that connect all the points of the roadmap. So now, from the start to the goal, we can plan a path that goes exclusively on the roadmap and that we know isn't going to collide with anything. How exactly you plan a path only on the roadmap, we will actually see an algorithm for that in the next lecture for mobile robots. But the important thing here is that once you have your roadmap, anytime somebody gives you, let's say that this is the goal, and let's say that this is the start, right? You hop onto the roadmap as quickly as you can, and then you plan a path exclusively on the roadmap that gets you from the start to the goal. Again, the power of random exploration, right? With only 10 points, we've done actually a reasonable job of covering this space. Most of the starts and the goals that somebody could give us, we will be able to hop onto the roadmap. And also the roadmap is fully connected. It can happen if your obstacles are really difficult, that your roadmap has two completely separate components and you cannot get from one to the other. It can happen that somebody gives you a start and you just cannot hop onto the roadmap. If either of those happen, then you just keep constructing your roadmap. You just go back to this point and you make your roadmap even bigger. Eventually, though, your roadmap will give you good enough coverage that from any start you can get to any goal exclusively on the roadmap. And again, the power of random explorations. RRTs, PRMs, they both perform very well in many problems for robot arms. Which to choose, that will depend on the subtleties of the problem or maybe which implementation you would have available. Again, I have highlighted here all the external calls that this makes. Again, you need a random number generator. The same idea, you need to check if a branch of your roadmap intersects an obstacle, which you do by discretizing, just like we did for RRTs. The only new thing is this call, find the path between start and goal going exclusively on the roadmap, and we'll have an algorithm for this in the next lecture. So let's recap stochastic motion planning. RRTs, PRMs, other algorithms, and there are many variations of these algorithms. Again, the one we've looked at here are just some possible implementations, which are nice in their simplicity. There are many possible variations of them. What's nice about this family of algorithms is that really the only thing you need is this ability to quickly check if a point in C space is legal or not. Most often that means, is it in collision? You might have other ways to define a point that's legal or not in configuration space. Maybe it's not that you're in an obstacle, maybe you're too close to an obstacle. Or maybe that configuration of the robot requires the robot to be fully extended, in which case it cannot support the weight of whatever it's carrying. There are other ways to define when a point in C space is legal or not. Most often that means, are you hitting something or not? So this is really the only thing you need to be able to run and execute one of these stochastic motion planning algorithms. A theoretical characteristic of many of these algorithms is that they are what is called probabilistically complete. It can be proven theoretically that if a path exists from the start to the goal, the algorithm will find it. Because again, the random nature of it can be scary at first. Wait a second, I'm going to just do random exploration and you're telling me it'll be fine. So the one theoretical guarantee is that if a path exists, it will be found in finite time. The flip side is that, well, you really don't have any guarantees. It's possible that that finite time will be very, very, very long. might be even longer than just doing an exhaustive search of all possible paths. So while you have this theoretical guarantee of probabilistic completeness, there are no guarantees in terms of how long it'll take. But the one thing that you do know from experience is that in practice, these algorithms work remarkably well for high-dimensional spaces. So if you have a robot that has 6 joints or 7 joints or maybe even more, and in general, a motion planning problem where you're searching for a path from a start to a goal in a high-dimensional space in the presence of obstacles, stochastic motion planning is known to perform really, really well. The other thing that stochastic motion planning makes no guarantees about is the quality of the solution. What do we mean by the quality of the solution? Well, maybe you don't just want a path. You want the shortest path. There's no guarantee that once RRT or PRM has found a path, that's the shortest path. In fact, if you just take the raw solution from the RRT and the PRM, it's immediately obvious that it's not the shortest because it contains many, many zigs and zags, and that's just the nature of random exploration. So you can eliminate most of those zigs and zags by just very simple post-processing. You just take your path and you say, hey, can I take shortcuts? I have all these points along my path. Can I just connect 2 of them directly and ignore everything in between? And if you can, then I'm just going to shortcut. So that improves the quality of the solution. Even after you post-process, there are no guarantees that you found the optimal solution. There might be an even shorter one. If you keep running the stochastic algorithm, if you just give it more time, maybe it'll find a better solution for you. You still won't know if that's the best you can do. All you can say is, you know what, I have this much budget available to me in terms of how long I can afford to let it run. I'm just going to let it run for that long. And if it finds a solution, great, and I'll take whatever is the best solution that it has found in that limited amount of time. For 6 or 7 degree of freedom robot arms in realistic problems with, obstacles that you can expect in the real world, generally high-quality implementations will find solutions in less than a second. If a problem is pathologically bad, where the robot really has to reach through a tight passageway, it might take a few seconds. Most problems you can expect to encounter for robot arms in 6 and 7 dimensions are tractable and solvable using this category of algorithms in just a few seconds.